Okay, Chem, we're going to go over Hess's Law one more time to make sure everybody understands the concept. Remember, Hess's Law has to do with the heat evolved or absorbed in a chemical process. This is going to be the same whether the process takes place in one step or several steps. So if two or more chemical equations can be added together to produce an overall, or what we called target reaction, the sum of the enthalpies of those given reactions will equal the enthalpy change of the overall reactions. This is called heat of summation. So remember, with Hess's law, some equations are known values that we can look up, or standard values, and some are unknown. So that's why we need Hess's law to add together known quantities to equal unknown quantities. So here's our steps. First, we're going to identify a target reaction. We'll evaluate the given equations with the known enthalpy values. And then we're going to rearrange and manipulate those equations so that they'll produce the overall reaction or target reaction. When we do that to the reaction, we have to do the same to the enthalpy values. So we can either multiply by a factor to get the desired coefficient, or we can flip the entire equation so that the products are in the reactants and the reactants are in the products. When you do that, you need to change the sign. So the next step is we'll check that species we don't need cancels and species that we do need are present and don't cancel. After we figure all that out, we can add the enthalpy terms, and we should get the change in enthalpy for our target or unknown reaction. Example 1. We're going to use these equations that are given to us at the bottom with the known enthalpy values to figure out the enthalpy change for 1 mole of water gas added to 1 mole of solid carbon yields 1 mole of carbon monoxide gas and 1 mole of hydrogen gas. This one's pretty straightforward. Yesterday we went from start to finish, so we'll do that one first. So we're going to say the first thing I need to fall into place is water. Remember yesterday we ignored water, but that was only because it occurred in more than one equation. We don't have that case here. So I'm going to look at the second equation. Equation 2 has water in the product side with a coefficient of 1. We need water in the reactant side with a coefficient of 1, so we're simply going to flip the second equation. Then we need carbon in the reactant side with a coefficient of 1. We have carbon in the reactant side with a coefficient of 1 in the first equation, so we will leave that be. So the only thing we need to do is flip the second equation. You'll notice the ones that we don't need, which are the 1/2 mole of oxygen on the reactant side, cancels with the 1/2 mole of oxygen on the product side. And we are left with things we do need, which is 1 mole of carbon on the reactants, 1 mole of water on the reactants, 1 mole of hydrogen in the products, 1 mole of carbon monoxide on the products. So everything's looking good. You just add those 2 enthalpy values up. In your calculator, it's negative 110.5 plus positive 241.8. Let's check out a problem that's a little bit more complicated. So here's our given equations. This time there's 3 of them. Now, last time we went from the start to the finish of the target equation. Let's do it a little bit different this time, where we would go use equation 1 first, then 2, then 3. Equation 1 has butane, which is what I need. I need 1 mole of butane, C4H10, in the product side. Equation 1 has 1 mole of butane in the reactant side. So the first thing we're going to do is flip equation 1. When I flip equation 1, I have to change the sign from negative 2657.4 kilojoules per mole to positive. Equation 2 has carbon in the reactant side like we need it, but it only has a coefficient of 1, and we need 4. So I'm going to take all of equation 2 and multiply it by 4. When I multiply the equation by 4, I also need to multiply the enthalpy by 4. Now let's distribute that 4 out. Equation 3 has hydrogen in the reactant side like I need it, but it only has a coefficient of 1. So I'm going to multiply all of equation 3 by 5. When I multiply equation 3 by 5, I also need to multiply the enthalpy by 5. Now let's distribute that out. Notice when you multiply the 1/2 mole of oxygen by 5, you get 2.5. So let's check out. We do have 4 carbons in the reactants, and we do have 5 hydrogens in the reactants. We also have 1 butane in the products. All the rest of that stuff needs to cancel out. So we have 5 waters in the reactant side and 5 waters on the product side, so those will cancel. In the reactant side, the oxygens, we have 4 plus 2.5, or 6.5 in the reactant side, and then we have 6.5 in the product side. Those will cancel also. The carbon dioxides, I have 4 carbon dioxides in the reactants and 4 carbon dioxides in the products. Those cancel. We're all good to go. Everything that I need is there in the right quantities and does not cancel. Everything I don't need is there in the right quantities to make sure they do cancel. So all I have to do in my calculator is type in plus 2657.4 plus 4 times negative 393.5 plus 5 times negative 241.8. Got to be super careful with these negative signs. And that gives me a final answer of minus 125.6 kilojoules per mole. That is what we call the enthalpy of formation of butane from the elements in their elemental state. It is negative, therefore it is an exothermic process.